You use tools like ChatGPT, translators, and image generators every day. But what actually powers them? In this course, we'll unpack transformers step by step, with minimal math and hands-on examples, so you can move from curious beginner to confident practitioner. Here's the roadmap for your journey. We'll start by grounding you in modern AI and sequence modeling. Then we'll uncover the core ideas behind transformers. Next, you'll build and use real models in practice. Finally, we'll connect everything to real-world applications and point you toward future learning. Think of this course as a guided loop: concept, intuition, practice, then reflection. We'll first build a shared language for machine learning, deep learning, and sequences, so the terminology feels natural. Then we'll develop a strong gut feel for attention and transformers without drowning in math. After that, we'll turn that understanding into hands-on skills with real models. To close, we'll zoom out, connect everything to real-world uses and limits, and help you decide where you want to go next. Treat this course like a workout plan tailored to your level. If you're newer, move steadily through the early modules. They build intuition you'll rely on later. If you're intermediate, skim the basics, then dive deep into exercises and projects. If you're advanced, cherry-pick topics as a refresher, but review the summaries so our terminology matches yours. Throughout, pause often, restate ideas in your own words, and reach out for help when you're stuck. We'll begin by stripping away the buzzwords and asking a basic question. What are machine learning and deep learning really? You'll build an intuition for how computers learn patterns from data, naturally setting the stage for understanding transformers later. Traditional software is like a long checklist. If this word appears, mark it as spam. Otherwise, let it pass. That works for simple cases, but it breaks as soon as spammers change tactics. Machine learning reverses the process. Instead of writing rules, we feed labeled examples. The model discovers subtle combinations of words, senders, and behaviors and keeps adapting, crucial for messy tasks like language, vision, or speech. Machine learning methods fall into three big families. In supervised learning, we show the model examples with the right answers, like labeled spam and not spam emails. In unsupervised learning, we remove labels and ask it to find patterns, like clusters of customers. In reinforcement learning, an agent learns by trial and error through rewards. Now let's zoom in on neural networks themselves. Think of a neural network as a big calculator that learns its own formula. Each neuron is a tiny decision maker. It takes numbers in, does a simple operation, and passes a number on. Weights act like volume knobs, turning some connections up and others down. By stacking layers of these neurons, the network can gradually build very complex transformations, mapping raw inputs like pixels or tokens into useful outputs like labels or the next word. Training a neural network is really a feedback loop. We start with random weights, so predictions are basically bad guesses. For each example, we compare the guess to the true label. The loss function turns how wrong into a number. Then an optimizer like gradient descent nudges the weights to reduce that loss. Over many examples and many passes, errors shrink, and the network's predictions steadily improve. Deep learning takes this idea further by stacking many layers so the model can build concepts step by step. A shallow network might only carve a simple, almost straight-line boundary between classes. Add depth, and early layers notice edges or basic word patterns. Middle layers combine them into shapes or phrases, and later layers capture objects, meanings, and context. That hierarchical representation is what makes modern language models and vision systems so powerful. Representation learning is about how a model turns raw data into meaning, layer by layer. For an image, the first layers notice simple patterns like edges and colors. Middle layers combine those into shapes and parts. Later layers respond to whole objects like cat or car. Text works similarly. Characters and tokens first, then phrases, then nuanced context. We never code these features by hand. They emerge automatically during training, and transformers are especially strong at learning these rich, context-aware representations. You can view the AI family tree as three big waves. First, classical machine learning. Algorithms that rely on humans crafting features, working best on clean, structured data. Next, early neural networks. They could learn their own features, but were shallow and limited by data and compute. Finally, the deep learning boom. Huge datasets and GPUs unlocked very deep models, enabling CNNs, RNNs, and ultimately transformers for complex perception and language tasks. Before transformers, RNNs were the default way to model sequences. Think of them as reading text, one token at a time, carrying a hidden state that summarizes everything seen so far. LSTMs and GRUs refine this by adding gates that decide what to keep, forget, or update, so long-term dependencies survive better. But there's a cost. Every step depends on the previous one. That sequential bottleneck limits parallelization and still makes very long-range context hard to capture, motivating attention-based models. Transformers sit in the deep learning family as sequence specialists. Instead of walking through a sentence one step at a time, they look at the whole thing and decide, for each word, which other words matter most. That global attention fixes the classic RNN problem of losing track over long distances, and it runs efficiently in parallel. Because of this, transformers have become the standard for language and are quickly taking over vision, audio, and multimodal tasks. So far, you've seen how we moved from rule-based systems to machine learning, how neural networks stack layers to learn rich representations, and how that evolution leads to transformers powering tools like chatbots and recommenders. Next, we'll zoom in on sequences, text, time, and context, and see why order matters so much.